Hello everyone, this is Rahul and today we are going to talk about phase transition behavior in knowledge compilations. This work was done with Professor Subhajit and Kuldeep Meel. So let's first talk about knowledge compilations. Now knowledge compilations are tractable yet succinct representations for propositional formulae. And the idea here is to first generate an efficient compilation for a given formula and then use it later to answer queries quickly in an online fashion. So for example, queries can be model counting or enumeration, which are actually exponential in the original CNF or DNF, but they run in poly time in size of the compilation. Now, this technique finds use in many areas, including formal verification, model-based diagnosis, and probabilistic reasoning. While a number of representations have been discovered in the past, we are going to look at some of the popular ones, DDNF, SDD, and OBDD for phase transitions. But the general behavior actually extends for all knowledge compilations under DNNF. Now, let's look at a bit about phase transition behavior. So, phase transitions are usually concerned with a sudden change in the behavior of a property of interest for an object pertaining to variations with spectral control parameter. Now, a popular example is water, in which states change with temperature. Now, this behavior has actually been observed for many more randomly generated problem instances. For example, in the NP complete class, we have KCNF SAT, CNF DOR SAT, QSAT, and many such problems. What's interesting here is that the complexity of solving the problem is also seen to peak at the same parameter thresholds regardless of the algorithm used. And we call this as phase transition behavior. And in this study, we will see how phase transition behavior is seen for knowledge compilations for the randomly generated KCNF formulas. Now, a classic example of phase transition behavior is for SAT for KCNF problems. So I will not go into much details here, but in this figure, on the x-axis, we are drawing clause density, that is number of clauses divided by number of variables. And on the y-axis, we have the runtime. And here you can see in the blue line that near clause density 4.3, you can see that the runtime of the solver increases tremendously as compared to nearby clause densities. And it's precisely at the same time that the phase of KCNF changes from SAT to unsat. So this again is an example of phase transition behavior at the time of phase change. Now, the study of phase transition behavior was very instrumental in getting a deeper understanding of KCNF problems, and even it has been very influential in the context of other CSPs as well. It was much later that their explanations came. We hope that our work here will inspire similar efforts in the future for knowledge compilations. Now, let's look at this in a little more detail. So, here are notations. So, a clause is non-trivial if it does not contain any repeated literals. Given clause length n, number of variables n, and clause density r, we have the random variable fk and rn, which denotes a Boolean formula in CNF with rn non-trivial clauses of length k, which are selected uniformly, independently, and without replacement. Now, KCNF here denotes the set of all possible Boolean formulas fk and rn, and the total number of witnesses are denoted for formula f are denoted by sharp f. Now here we also have a newer random variable, and we have a new term here called as solution density alpha, and we define the random variable gkn to the power alpha n as a randomly chosen Boolean formula from KCNF with n variables and seal of 2 to the power alpha n satisfying assignments. Note here that KCNF was the set of all possible Boolean formulas of a particular length. Now we have XL and TL as the number of nodes, denoting the number of nodes and compile time for the compilation formula F to target language L, and E of X denotes the expectation of random variable X. So now let's look a bit about design of experiments. So in this paper, we dive deeper into the size and compile time behavior for DDNF, SDD, and OBDD compilations owing to their wide range of applications. Now, as a direct way to generate GK and CRISPR alpha and given alpha is unknown, basically we don't know how to generate a problem instance given a number of solutions. So to study that, we actually look at the size and compile time behavior for individual instances that are generated by varying R. And now talking about the variations that we consider as part of our study. So we have taken a number of variables, we vary the number of variables mostly from 20 to 70 and up to an exponential number for a subset of cases. We are varying the clause lengths from 2 to 7. We are looking at DDNS, OBDTs and STDs, and we use the respective state-of-the-art knowledge compilers for this purpose. Now let's look at the behavior with clause density. So here in these figures, on the x-axis I am plotting clause density, while on the y-axis I have plotted nodes and the compile time respectively. And here you can observe that as clause density reaches 1.8 and 1.9, we see a sudden increase in the number of nodes and the compile time respectively, and this resembles very close to the phase transition behavior. Now we see similar. Now as we increase the number of variables, we observe that the peak even gets sharper and sharper, and the behavior extends simply to STD and BDDs as well. Note that here the compile time for BDD is a bit more involved, and we have discussed this in the paper. However, I'm omitting it here for lack of time. Now if you look at the behavior with changing clause densities, now here you can see that even though the peak clause density for phase transition behavior has changed, but the overall pattern of sudden increase in the hardness or compile time remains the same. Now based upon this, we draw the conjecture that for every integer k greater than or equal to 2 given a number of variables n in a target language L, that is a subset of Pn and F, there exists a possible real number Rk such that for each pair R1 R2, if R1 is less than R2 is less than Rk, then the expected number of nodes for R2 is greater than Rk, and on the other hand, when R1 is less than R2 and both of these are less than Rk, the expected number of nodes for R1 is greater than R2, basically saying the same thing, that there is a sudden increase in the compilation, there's a sudden increase in hardness near the phase transition threshold. Now we have looked at clause lengths, but this begs the question whether clause length is the only factor here which is affecting hardness. We know that knowledge compilations can be seen as a representation of the solutions, so a natural extension of the question is that whether the number of solutions also affect the size of the compilation. And so to investigate this, here we plot on the x-axis solution density and on the y-axis number of nodes. Now in this graph, what we are considering is that in this graph we are taking instances generated for clause length 3, and for each such instance we look at this number of solutions, calculate its solution density and plot it in the graph. Now notably, we know that expected solution density is fixed with clause density. However, still we observe that as we vary the solution density, there is a significant change and a gradual change in the size of the compilation, and this suggests that the number of solutions is also an important factor affecting phase transition behavior. So now let's look at solution density in a bit more detail. So similarly, plotting the figure, since we don't have a direct way of getting a problem instance given a number of solutions, so here we are looking things slightly in reverse. That is, first we generate instances by varying clause density, and then for each such instance we plot the solution density and the number of nodes in the figure to get an idea of the behavior with respect to solution density. So here we can observe that around 0.6, around solution density 0.6, there is a sudden increase in the number of nodes and the compile time for DDNF, and this behavior is very similar as in the earlier case. That is, if we increase the number of variables, then this peak just gets more and more sharper, and the behavior extends to the other compilations STD and OBDD as well. Now, looking at the behavior with changing clause lengths, here you can see that with varying clause lengths, while the solution density for the peak phase transition threshold changes, but the overall behavior persists nonetheless. The conjecture here that we draw is that for k greater than or equal to 2, given the number of variables n and a target language L that is a subset of Pn and F, there exists a possible real number alpha k such that for every pair alpha 1 alpha 2, if alpha 1 is less than alpha 2 is less than alpha k, then expected number of nodes for alpha 2 is greater than alpha 1, and on the other hand, if alpha k is less than alpha 1 it's less than alpha 2, then the expected number of nodes for alpha 1 is greater than alpha 2. Basically saying the same thing, that the size of the compilation and the runtime increase towards the phase transition alpha. Now again, so having looked at both the solution and clause densities, this is a natural extension to see if there is something much more subtle that is at play here. So to investigate further, we plot solution density against clause density in a heat map to show how the size and the runtime varies. Now here you can observe that for in the first figure, when clause density is restricted from 0 to 0.1 to 1.4, if I fix a clause density, then there is no variation in color with respect to solution density, and this allows us to say that the varying solution density seems to have minimal effect on size of compilations for low clause density. Now for the second figure, in which vary clause density from 3.1 to 5, you can observe that as I fix a clause density, the variation in color pertains with change in the solution density. On the other hand, if I fix a solution density, the color remains almost the same. This suggests that for high clause density, solution density has a dominant effect on the size and there is minimal variation with clause density. Now looking further, so at the asymptotic complexity, now we know that the size and runtime of compilations are exponential in the number of variables in the worst case. However, for practical applications, we are much more interested in a precise relationship, as it's the size that plays the crucial role in many applications. Now, while it is known that the exponent increases towards phase transition clause density, it is not clear if the exponent is linear or sublinear in the number of variables and whether this behavior changes with changing clause density. Note that by exponent I am thinking of the number of nodes and compile time as 2 raised to the power function of b of rn, and we are looking at variations for t. So to investigate further, we plot the log of number of nodes divided by variables with varying clause density and number of variables, and you can see that from the first figure, independent of r, as we increase the number of variables, the log of number of nodes over variables decreases. And looking this behavior for a very high number of variables for smaller values of r, we can see that as the number of variables increase, the log of number of nodes divided by variables decreases monotonically, and this allows us to draw a conjecture that as limit tends to infinity, then the log of expected number of nodes divided by n tends towards a constant. However, we cannot say whether this constant is 0 or not, and this constant depends upon the clause length, clause density, and the compilation target language. Looking at the similar behavior for compile time, here things are quite a bit interesting, because here we observe that the compile time, in case of compile time, the log of runtime divided by variables increases monotonically with the number of variables, and since we know that in the worst case the runtime is exponential here, so here we are able to say that as limit tends to n tends to infinity, the expected amount of time divided by number of variables converges to a constant, is equal to a constant. In other words, expected runtime is equal to theta of 2 to the power cn for state of the art compilers. Here's one more behavior which is usually observed in the context of phase transitions, and that's polynomial to exponential phase transition. Now, looking at the polynomial to exponential phase transition, now in the past, Gao has shown the possibility for polynomial to exponential phase transition for small values of r greater than or equal to 0.3. However, we scaled the experiments to a much larger number of variables, and here we observed that even for smaller values of r, if we look at a very large number of variables, then there is a change in the slope of the log-log graph. The idea here is that the relationships of the form y is equal to a x raised to the power k appear as straight lines in a log-log graph, and we observe in the graph that around the number of variables 10 to the power 4, the slope of the graph increases, and this allows us to say that for every r, for every clause density, expected number of nodes is at least polynomial in n. Now, to sum up our work here, we demonstrate phase transition behavior in knowledge compilations with respect to clause density and novel parameter solution density. We observe that for low clause densities, varying solution density has minimal effect on the size of compilations. In contrast, for high clause densities, solution density has a dominant effect. There is minimal variation with clause density. And in terms of complexity of compilations, we see that the expected size is at least quasi-polynomial, and the expected runtime is exponential in the number of variables with varying clause density for state-of-the-art knowledge compilers. Now, here are some of the references that we cited in the paper and presentation. Yeah. Okay. So thank you all, and please feel free to ask any questions. Thank you.